computer and your other thing have record capabilities. Okay, it's 4:31, so I'll start introductions, and then people might continue to file in, and that's fine. So welcome everyone to our next Zoom Olivetti seminar. So again, there is a feedback form in the chat, and we'll post it at least one more time in a couple minutes. So you can open that up and fill it out during the meeting or just after, and then we will get everything to Chaitanya afterwards, and it's anonymous. So do that if you can. Otherwise, we'll get started. So today's speaker is Chaitanya Tappu, and he will be telling us about hyperbolic structures on surfaces and Thurston's earthquake theorem. Okay, take it away.
I just want to say you need to enable screen sharing, I think.
You don't have permission? Everyone should have screen sharing permission. Let me.
Oh.
When I click it, it says I don't have permission.
Okay.
Yeah.
I thought I made that a permanent feature of the meeting, but I didn't. But now you should be good to go. Sorry.
Okay, awesome. Okay, thanks for coming, everyone. Okay, let's start. So I want to just start with a question. If you remember this game, I hope this video plays all right. This is what I played a lot as a kid. I don't know if everyone did. And well, this is a retro game called Snake on Nokia, if you never played this. And the goal of this snake is to eat up these sorts of I don't know, apples or whatever food and grow in length. Anyway, so so what I want to say is, the question is, what sort of world does the snake live in? What is the geometry of this world? And oops, dang, that gave the answer away. Okay, so as you can see, the stuff on the screen is a square or a rectangle. And what happens is when the snake goes out through some portion of the bottom of the screen, snake comes back inside the screen from the top. And so if the snake goes from here, it goes out from here, it'll come back out from the other side. And similarly for the for the vertical sides as well. And so that is to say, we are identifying the two opposite sides of the square. So let me try to color these. I hope this works. Yeah, great. The red sides are identified, and so are the blue sides. And from topology class, we know that this is a surface called a torus, which is this picture that I've drawn over here. Which one? Yeah, this is the torus. Okay. So that's the topologically torus. That's the answer to the question. But wait a second. There's something more to it, right? There's some more features of the world that the snake lives in that we haven't yet said by just saying that opposite sides get identified. So question, can someone say what is something that we have not used yet? what are more features of this world? You can like unmute and say something if you want to. So we already said it's a rectangle with opposite edges identified, but there can be more structure to this space. And if you have any guesses. Okay, here's one thing that that you can have. So there is more to it. So for one thing, the snake takes a fixed number of steps to go from one end to the other. How am I going to phrase it? So if the snake takes a fixed number of horizontal steps to go from one point and return to the same point. And that is the length of this side, right? If it takes a certain number of horizontal steps, it comes back to its original starting point, and similarly for vertical steps. This is a feature. So there's some sort of distance on this space, and the snake can count it. It can count how many horizontal steps it has to take to get back to its original point. And so this suggests that there is a Riemannian metric as well. And the Riemannian metric is just the obvious one. For this torus, it will be dx squared plus dy squared, where x and y are coordinate functions like that. And in these coordinates, why does one actually get a Riemannian metric? The recipe is if you start with a rectangle 0 comma a cross 0 comma b, say, and glue opposite edges. The gluing of opposite edges is not just arbitrary. It is with a specific gluing map, and the gluing map is x comma 0 maps to x comma b. So if this point is x comma 0 over here, this point is x comma b, and this is mapped over here by the gluing map. And x comma 0 mapping to x comma b is an isometry of the Euclidean plane. And this is why we can get a Riemannian metric on the torus, because we're gluing using isometries. Okay. Okay, so so another thing is that the universal cover of this torus is R2, and right. Okay, so what if you started with some other sort of shape and glued opposite sides together? So I have something over here, and what if I glue these opposite sides. As you can see, again, the gluing maps will be the same sort of isometries, but they'll be slightly different. So here, this gluing map will be of the form x comma y maps to x minus alpha comma y plus b. But it's still an isometry. So even on this weird parallelogram, if you glue opposite sides together, then you get a flat Euclidean torus. But the two tori that I just constructed are different. And the reason that they are different is that so these tori are different. And the reason is the lengths of blue sides are different. Blue circles. So if we keep track of the two circles that we have to cut along in the torus to get back our square, we are keeping track of what circles over here, these two circles that we have to cut to get back our parallelogram or rectangle that you started with. If you keep track of their lengths, you can see that these two tori are different. And a question is, well, so how do you change from one torus to another non-isometric torus? And one way of changing this structure would be to slide along the red edge. And that's what I've drawn over here. So the red and blue lattice is the covering map on of R2 onto the first torus, the rectangular one, and the red and orange lattice is a covering map for the second torus. And as you can see, I'm basically taking the vertical lines and just sliding them along the red curve. So I'm taking each of these pieces and they're being slid across from each other. And this is an earthquake.
You're about 15 minutes in.
Okay, great. Okay, so this is what an earthquake is supposed to be. Well, Thurston actually proved it, did earthquakes for hyperbolic surfaces, and but I just showed you an example for Euclidean surfaces. It would be a good question to do the theory of earthquakes for Euclidean surfaces. Okay, so let me introduce the hyperbolic plane. There are two models of the hyperbolic plane that one should really know. One is called the upper half plane model. So this is x comma y in R2 with y greater than 0, and the metric is dx squared plus dy squared divided by y squared, and there is the Poincare disk. So in the Poincare disk, so this is x squared plus y squared should be less than 1, and the metric is 4 times dx squared plus dy squared divided by 1 minus x squared plus y squared squared. No, not squared. Yeah. Okay. Anyway, you don't need to know what this metric is, but what is interesting about this is that this has curvature -1, constant curvature -1, whatever that means. What are geodesics in this space? So the analog for straight lines in Euclidean geometry are these sorts of circles that are orthogonal to the boundary. So let me call the hyperbolic plane H2, and the upper half plane and Poincare disk are two charts on H2, and the boundary of the hyperbolic plane is this. So this, in the upper half plane model, it is the real line union one point at infinity, and in the Poincare disk model, the boundary of the half plane is the circle S1. So boundary is homeomorphic to S1. So the boundary is not part of the hyperbolic plane, but it's just something that compactifies the space. Okay, and I should have said, so these are perpendicular in what you see. That is, they're not really perpendicular inside the space because the boundary is not part of the space. All right. If you want to have a look at hyperbolic space, here's a good game. This was designed by Jeffrey Weeks. If you go to geometrygames.org, you'll see some games based on all sorts of geometry. And let me just zoom in. Here's a mouse in hyperbolic in the hyperbolic plane, and it's in a maze and wants to get to some cheese. And what you see here is the hyperbolic plane, but it's also tied by the fundamental domain of some compact surface. And as you can see, these lines here are pieces of geodesics. What else did I want to say? Yeah. So so the metric goes to the metric becomes really large. The factor, this denominator factor in the metric becomes really large as you go to the boundary. So even though what you see near the boundary is very small, it really has the same sorts of lengths as these maze pieces over here. They're all congruent. Even though the stuff at the boundary looks smaller, it really has the same size. Okay, so that's the hyperbolic plane. I want to say something about the isometries of the hyperbolic plane. There are there are three kinds of isometries of the hyperbolic plane. The first one I'll call elliptic. So these are analogs of rotations in Euclidean geometry, and this is how they appear. So the circles that you see over here, oops, I don't know if I can draw with this. Okay, never mind. So these circles are actual circles of some radius in hyperbolic space. They're Euclidean and they are centered at this red dot. And as you can see, they are still, they look like circles to you, but whatever looks like their center to you might not be the actual hyperbolic center. This is in the upper half plane model. Okay, so these are like rotations. Then there are parabolic elements, isometries. Let me see isometries. So parabolic isometries somewhat look similar, but why can't I just, yeah. But as you can see, the red point is now somewhere at infinity. So these aren't really circles. Points don't move along circles, but they move along horocycles. And yeah. And the most important sort of isometries are called hyperbolic isometries. And those are the ones you sort of need to know. So hyperbolic isometries are the analog of translations. So now there are two red points, and the two red points on the boundary determine a geodesic in the hyperbolic plane. And what is happening is something like translation along that line. Okay, the other so the geodesic is has a certain number of marked points along it, which are the blue points, and all the other circles that you see are not actually geodesics. They're not perpendicular to the boundary. But what's happening is you still call it translation along the geodesic. So yeah, okay. Are there any questions about how hyperbolic isometries look like? Let you stare at the video for another 5 seconds. So this was what you saw over here was the translation along a geodesic that looked like this. I want to show you just an actual formula for the translation along a vertical geodesic. So if this is the upper half plane, let me call it U, and one geodesic could be the line 0, y, where y is greater than 0, which is this, and the hyperbolic translation along this geodesic is given by the formula z maps to lambda times z in complex coordinates, or maybe x comma y maps to lambda x comma lambda y, where some lambda is some positive real number. So a point would get mapped to something collinear with the origin. Okay, and this line, this geodesic is called the axis of the hyperbolic isometry. Okay, if a red point gets moved over here, then this distance is equal to log of lambda, and log lambda is called the translation distance. I also want to show you how parabolics look like. So parabolics in this picture are given by z maps to z plus 1. Okay, so if you quotient H2 by these parabolic by such a parabolic isometry, in other words, if you take this piece of the hyperbolic plane and identify the two edges using the this above formula, then since the parabolic isometry is an isometry, you would expect that on the quotient surface, the quotient surface can also be given a hyperbolic Riemannian metric, and that is exactly what happens. So the quotient here looks like this. It has a cusp at one end, and it flares at the other end. So the flaring is because this distance is much larger than any distance above. Circles at the bottom of this annulus have much larger length, because the metric scales as y squared. So as y becomes smaller, the length grows larger and larger. All right, and the quotient of by the hyperbolic isometry looks like this. So how am I going to write it? Yeah. So it has flares on both sides. Okay. In general, you can construct hyperbolic surfaces by by more gluings. And so here is another example. This is a genus 2 surface. So for that, you take a hyperbolic octagon, and you glue opposite sides according to an identification like this, and that gives you a genus 2 surface. And yeah, and because you glued them using isometries, you get a hyperbolic surface. You also have to check something, some technical condition, like the sum of the angles of the octagon is 2 pi. And this sum of angles becoming equal to 2 pi is possible only in hyperbolic geometry, not in Euclidean geometry. That's why on higher genus surface, compact surfaces, you can not put Euclidean metrics, but you can put hyperbolic metrics. Okay, also we are going to keep track of these curves. So we're going to keep track of these curves, which we need to cut along over here to get back a representation as an octagon. Okay, so so just like before, where we had a torus and then we sort of slid past some curves and made another torus, and we can do so with hyperbolic surfaces as well. So one possible example is, take a geodesic in take a geodesic somewhere along here, and then cut along the geodesic, and what you get would be two surfaces. So, and let's say this point was identified over here, and then you twist and you glue back. So after you do all this, you'd get something that looks different. So if you glue it with a twist, the 2 points that were identified at in one position are now some distance apart. So this has changed the hyperbolic metric on the surface, in the sense that so which curve can I draw? So let me draw the green curve from here. So the green curve that looked like this before, now looks like, how does it look like? It looks like this, but here it undergoes some sort of cutting, and again it will undergo a bit of cutting and come back. Right. So keeping track of this green curve is called keeping track of a marking on the surface. Marking means keeping track of green curve and others. So these two hyperbolic surfaces are different marked hyperbolic structures. And that's what Thurston's theorem really is. Thurston's theorem is that you can get from any hyperbolic structure to any other by quaking. along geodesics. And let me try to make this precise now. So for that, I'm going to give you a precise definition of what a marked hyperbolic structure is. And then I'm going to tell you the stuff about how earthquakes change hyperbolic structures. So first I should tell you what a Fuchsian enlargement is. A Fuchsian enlargement is essentially adjoining some stuff to a hyperbolic surface. In order to make a surface with a boundary. So if you have a cusp, there is, you don't add anything here. But if you have flares, add a circle. And if you have two flares, then add two circles. So if this M was my hyperbolic surface, then its Fuchsian enlargement is, topologically, it is just the cusp along with this circle, which is a surface with a boundary. It's homeomorphic to a punctured disk, in fact. And the Fuchsian enlargement of this surface, this hyperbolic surface, is a cylinder. So let's call this M bar. If this is N, this is N bar. And whatever you just added is called the Fuchsian boundary. So this is the boundary of M bar. This is the boundary of N bar. And the boundary just keeps track of where the hyperbolic surface grows very large, the Fuchsian boundary. Okay. So here's a definition of a relative hyperbolic structure. Suppose M is a surface and M bar is its Fuchsian, Fuchsian enlargement with respect to a hyperbolic metric. Then a continuous relative hyperbolic structure. I should also say marked. Relative hyperbolic structure on M comma the boundary. So continuous, the relative hyperbolic structures are defined not for a topological surface, but a topological surface plus this possible Fuchsian boundary is a homeomorphism. So it's given by a homeomorphism M bar to X bar, where X is a hyperbolic surface with Fuchsian enlargement x bar, and two such homeomorphisms are equivalent if they give you the same marked structure. So what does it mean to give the same marked structure? If it means there is an isometry, oh, that's not how to put it. There's a commutative diagram that looks like so. If you have two homeomorphisms, one to x bar and one to y bar, then they give you the same marked hyperbolic structure. If there is a homeomorphism alpha is a homeomorphism, and alpha restricted to x from x to y is an isometry. And alpha of phi is homotopic to psi. So in some sense, we're looking at homeomorphisms, but if you change that homeomorphism by a if you just homotope that homeomorphism to some other homeomorphism, you still get the same relative hyperbolic structure. That's what's meant by keeping track of the marking. Okay, so what does this mean for the hyperbolic plane? The Fuchsian boundary, the Fuchsian enlargement of H2 is just its union with its boundary. So it is the closed disk. So this part is included in Fuchsian enlargement. And in the Poincare disk model, the boundary is the part that is the Fuchsian, just the usual circle, which is the boundary of the disk, is the part that is included. Okay, so what does this say? If you look closely at this definition, we are thinking about the topological type of our surface is the disk. Is the open disk D with boundary, the boundary of D is just the circle. And so we're looking at homeomorphisms from D bar to the completion of H2 up to homotopy. But homeomorphisms of the disk to itself are basically up to homotopy are determined by the homeomorphisms of the circle at the of the circle at infinity. So they are determined by homeomorphisms from the boundary. So this is S1 to the boundary of H2, which is also S1. And there is this pre-composition, post-composition condition of alpha. You could post-compose with an isometry and still get the same hyperbolic structure. So the set of, so you need to quotient by the set of isometries of the hyperbolic plane. So the set of relative hyperbolic structures on H2, comma del H2 bar is the set of homeomorphisms of S1 modulo PSL to R, which is the isometry group of H2. Okay. Okay, so what's an earthquake and how does it allow you to change this hyperbolic structure? So earthquake is twisting along the geodesic. Unlike, I'm going to focus on the case of hyperbolic planes right now. So unlike compact surfaces, the hyperbolic plane does not have any closed geodesic, a geodesic that comes up and intersects itself. So we look at just infinite geodesics. So a geodesic, and if you want to quake along lots of different geodesics at once, you look at that. The precise way of saying that is by using geodesic laminations. A geodesic lamination is a collection of disjoint geodesics whose union is a closed set. So, for example, you could just take a finite collection of geodesics that are not intersecting. Another example could be, which is this example can be slightly unnerving if you've seen surface diffeomorphisms before, is just all the geodesics that are parallel to a fixed geodesic. So this consists of all geodesics perpendicular to blue 1, and they fill up the whole hyperbolic plane, which is slightly not what one might be used to. Okay, so what's an earthquake on the plane? This geodesic lamination separates H2 into leaves, which are the geodesics, and gaps, which are complementary regions. So for example, this is one gap, and here is another gap. So an earthquake is an earthquake sourced on a geodesic lamination lambda is a map E from H2 to H2, which is bijective, and such that for any leaves or gaps A and B, E restricted to A is an isometry. Of is restriction of an isometry of H2, and if you take the comparison isometries, so this is a comparison isometry between A and B. this is a hyperbolic isometry. Whose axis separates A and B. And also translates to left as seen from A. So do I have space for, okay, I need to go down for the example. So here's a simple example of an earthquake on the hyperbolic plane. If I take the geodesic lamination to just consist of a single vertical line, let's call that x equals 0. This is lambda. Lambda is the geodesic lamination. Then there are three complementary regions. One is the left hand side. So this is number one. There are two complementary regions, and the total number of leaves and complementary regions is 3. And I should tell you what the earthquake map does to each of them, right? So in the complementary region 1, let's take the earthquake map to be identity. In the complementary region 2, you can take the earthquake map to be something like 2x comma 2y. So that's a hyperbolic isometry. That's the restriction of a hyperbolic isometry on this lamination. And the stuff on, say, the third side is 4x comma 4y. Okay. If you compute comparison isometries, let's say E restricted to 1 inverse composition with E restricted to 3 is just xy mapping to 4x comma 4y. And as we saw before, that is exactly the hyperbolic isometry that translates along the red geodesic, and it translates upwards. So if you view from the side of E1, it translates to the left. Okay, and so this is an earthquake. What is the image of a geodesic that looks like this? The image of that is just the same up to some point, and then it gets translated somewhere, and then the rest of on the right side, it gets translated even further. So yeah, so E maps the gray geodesic to the broken geodesic on the right. So as you can see, an earthquake map is typically not continuous. There are some cases in which earthquake maps can be continuous. But whatever be the case, E extends to a homeomorphism of the boundary. So the boundary, remember, is just a circle. Right. Okay. So every earthquake and a homeomorphism of the boundary is exactly what a hyperbolic structure, a relative hyperbolic structure on the hyperbolic plane is, right? So if I had disk closure mapping to hyperbolic plane under phi, and I chose E tilde, which is the stuff at the boundary coming from the earthquake. Then the composition would give E composed with phi. This is another relative hyperbolic structure. Right. So this is how earthquakes change relative lead to changes of relative hyperbolic structures. And so now I think I can state the earthquake theorem. Theorem, Thurston. Any two relative hyperbolic structures on H2 are related by an earthquake, and it is unique except where it is discontinuous. More precisely, or alternatively, this is almost the same statement written in a slightly different language. Given any orientation preserving homeomorphism of S2 of S1, there is an earthquake E such that the extension E tilde is equal to F. Right. So okay, so this tells you how to change between hyperbolic structures, and if you any compact hyperbolic surface, or just about any hyperbolic surface, has universal cover equal to the hyperbolic plane H2. So if you do all of this equivariantly, you get corresponding statements for any hyperbolic surfaces. And the set of all relative hyperbolic structures is called the Teichmuller space of the surface, or the hyperbolic surface. This construction of the earthquakes and the extension to homeomorphisms of S1 gives one way of topologizing Teichmuller space. Yeah. So one of the questions that I'm sort of trying to figure out is, if you look at, I just gave you one example of an earthquake, and that was very simple, consisted of just one geodesic. What about a lamination like this? What are all the earthquakes sourced on this lamination? And yeah, I think that's all I wanted to say. Yeah.
Excellent. Thank you. Does anyone have any questions? If so, you may unmute yourself and ask. Okay, it looks like that's a no. So I will just say Perry has put the feedback form in the chat again. So again, if you could just take a couple minutes and fill that out. It is really useful to get like feedback from your peers on this type of thing. And then I'll say Max Lipton is giving our talk next week on electrostatic knot theory, which sounds exciting because I only know those words separately, essentially. Otherwise, we can say thank you again, and I will see everyone next week or later this week.